Hi guys, my name is IBM. A lot of you have been asking me to record more paper fives, and today I decided to record paper 5 planning, analysis and evaluation. This is 970251 October November 2023. So without wasting time, I would like to take you to the question paper. So here is the question paper. It's 970251, that is October November 2023. The paper is 1 hour and 15 minutes. I may use more time, you never know, but I'll try my level best to save time. So you are used to the instructions. You can print the paper and try to plan and maybe follow my videos after your plan and see what you missed out in your plan. So this is the question number 1. Two coils C and D are placed with their axes on a straight line as shown in the figure. A resistor of resistance R is connected in series with the coil C. A changing magnetic flux of frequency F in coil C causes an electromotive force E to be induced across the terminals of coil D. So we know an EMF is going to be induced in the coil D. So the best thing would be to increase this, the induced EMF. We would put this onto a soft iron core. So this is going to be soft iron core. Okay. So it is suggested that E, which is the induced EMF, I must measure induced EMF in coil. So I must put here either an AC voltmeter or a cathode ray oscilloscope or an oscilloscope. So me, I'll put an oscilloscope this side. I'll put an oscilloscope to measure the induced EMF. And remember, how do we measure? How do we find the EMF, or how do we find V or voltage? From an oscilloscope, it is actually the Y gain times the vertical distance. Y gain times the vertical distance. Then on this side, I need the source. It is suggested that E is related to F by that relationship. So I'm investigating E and F. F is the frequency. I can easily change F, which results into a change in E. It is hard for me to change E to cause a change in F. So E is going to be the independent. E is going to be the dependent variable, and F is going to be the independent variable. Okay, so this side, I must ensure if R does not remain constant, then it means it affects E. So I must ensure that R is constant. I can measure R by using either an ohm meter. I could put here an ohm meter, or I could put an ammeter here, and then I put a voltmeter here. So I'll choose an ammeter and a voltmeter in the place of an ohm meter. Okay, so to measure R, and I'll find R from V over I. Okay, then I need to produce a frequency. You can use a frequency generator, but I will use an AC power supply this side. I'll just use an AC power supply. I cannot use a DC supply, so an AC power supply. And of course, so this is AC power supply. So if I want to find the frequency F, then I will add, I'll put a cathode ray oscilloscope again across this coil. So this is going to be a CRO or an oscilloscope. On the oscilloscope, I'll find V on the oscilloscope. That is the amplitude of the input AC supply across the coil and R. So I'll measure V. Of course, V is going to be the Y gain times the vertical distance. Then I'll also measure frequency from frequency equals 1 over period. And the period is, of course, the time-based setting. The time-based setting times the horizontal distance L on the cathode ray oscilloscope. Then, so it means I now know I have, I must also ensure that the coils remain a fixed distance. So I will clamp my coils onto a bench. So to ensure that the distance remains constant, I will clamp them onto a bench. or something which is on the bench. So this is going to be the bench. I'll clamp these coils on the bench so that the distance between the coils remains constant. Okay, so other things I will add them in the essay to make improvements. So we are planning an experiment to test the relationship between E and F. And in our arrangement, we should explain how the results could be used to determine values of P and Q. So we shall see the procedures. We now know most of the measurements to be taken. The control variables, we shall make sure V remains constant, R should remain constant, and we should also ensure that the distance between the coils remains constant. The distance of the coils remains constant. We should also ensure that the number of turns of the coil remains constant because all these ones would affect the induced EMF. Then analysis, which graph shall we plot? So we have E equals to P F power Q times V divided by R. When you see one of the variables having a power, then you introduce natural log, or you introduce log to base 10. So if I say ln of E equals to ln of P F power Q times V over R. So if I open this, I have that ln of E is going to be Q times ln of F plus ln of P times V over R. So I'm going to plot a graph of, the graph I'm going to plot for analysis is going to be ln of E versus ln of F, which will give me the gradient as Q, because you compare this with y is equal to mx plus c. So this means the gradient is Q. Then the y-intercept is going to be ln of PV over R. This graph will be a straight line that will pass through ln of PV over R. So to find the P, we shall say P is going to be equal to, this will be E, because I used the ln, so it will be E power the y-intercept. Then I multiply this by R divided by V, making P the subject. So that will be P and Q. This is going to be a straight line. The gradient is Q, the y-intercept is that. Then safety precautions here could be related to hot wires, which would cause burns from hot wires. And for burns from hot wires, I could use gloves, rubber gloves. So it means I have a sketch of how my experiment is going to look like. Okay, so I can start by writing out what is going to be in this experiment. So I will say in this experiment, I will start from the second line. I leave this for the diagram. So in this experiment, so I've said F is the independent variable. F is the independent variable and E is the dependent variable. Alternatively, you could simply say vary F. I'm saying, or you could say vary F and measure E. You would say vary F and measure E. Don't say both at the same time. If I say F is the independent variable and E is the dependent variable, I don't again repeat myself by saying vary F and measure E. Okay. So I will also keep, I have mentioned the quantities that will be constant. I will keep V and R constant. And of course, I'm going to fix the coils I'll clamp the coils on the bench to ensure that the distance between the coils remain constant. I'll keep the number of coils, I'll keep the number of turns on each coil constant. Throughout the experiment. Okay, so I also said I'll clamp the coils on the bench. Of course, I just want to mention that why I'm going to clamp the coils in the bench, because I want the distance between the coils to remain constant. So I will also clamp the coils on the bench to ensure that the distance between the coils remains constant. What else is very important here? Of course, I must remember I need the induced EMF to be large enough and measurable. So it means I'll place the coils closer, and also make sure V is large enough, and also make R as small as possible. Because from the equation that we are using, a large value of V will make E big, and a large value of R would make E to be small. So to make E as large as possible, I will place the coils closer. I'll place the coils closer. I'll increase or use a large value of V, or increase V, or make V bigger, and also make R as small as possible. The resistance should be smaller in order to ensure that E becomes bigger. Okay, let's first draw the diagram. Let me first draw the diagram here. Normally, the first thing you should always draw is the table or the bench, so that you have your setup is laid on the bench. So I'll have my table here. My diagram may not be extremely beautiful like yours, but I try my level best. So this is the bench. So I'm going to clamp my coils on the bench, so I can put them even on a sliding scale, where I can always check to see that the distance has remained the same. So I can put here a ruler or a scale which slides in form of a ruler. So remember, I'm going to put these coils on a soft iron core, so I have to draw here a soft iron core somewhere. Okay, so let me sketch coil C and I should put here coil D. Okay, so I'm trying to clamp these coils onto the bench, so I'll put here a clamp which holds these ones in this kind of shape. Okay, so this is coil D and this is going to be coil C. So this coil, for this coil here, I'm connecting it to a CRO, which I'm putting this side. So normally my students do that for a CRO. That's what I'm doing here. I'm just doing what normally my students do for a CRO. Okay, so this is oscilloscope. Or you just write there CRO, cathode ray oscilloscope. Then on this side I have to connect a resistor here, fixed resistor, and I need an ammeter. Then I'll add a voltmeter across this fixed resistor so that I am able to find the resistance R. Okay, so this is going to go to power supply, which is actually an AC power supply. Then I will now add another. I could put it this side on the bench, or I could just put it hanging that in space. So let me put another CRO here on the bench, but you can put it anywhere. So I'm putting this CRO here. It is across. So this is another oscilloscope. So I'll call this one, let me call this one oscilloscope A. And I'll call this one oscilloscope B to distinguish the two, because A is going to give me both a V and F, and B is going to give me E. So here I have an SC supply, which is represented like this. If you are not sure if that is the symbol for SC, then you can say SC power supply. You can't use DC here. So most likely this voltmeter, this is going to be an SC ammeter, and this is also going to be an SC voltmeter in most cases, so as to measure the ones I'm using here, because the current is, or the supply is alternating. So that is, I think this is a very beautiful circuit, which gives an impression of someone who knows what they are doing. Okay, so now I can continue with my SC. Having seen how the circuit looks like, or how the diagram would look like, I can now continue with my SC. Okay. So number one or number two, this was all step number one in this experiment. So now I'm going to start the real experiment. So step number one, I'll label it number one. So I will now, oh, I didn't include the switch. I need a switch here, because if it gets hot, I must turn off and allow it to cool down. So I need a switch. Okay. So this is my switch, which is very important. So I will now close the switch. I will now close the switch and determine R. So how would I determine resistance? I will determine R from R is equal to the PD across R divided by the current in R. That will give me the PD, I mean the resistance R. Then step number two, I will determine V. I will determine V from oscilloscope A. That's why I labeled them A and B. Oscilloscope A. And how will I determine V from oscilloscope A? From V, of course, V is going to be Y gain times the vertical displacement or vertical distance on the oscilloscope. Okay, so having determined V, remember V should remain constant throughout the experiment. Then step number three, I will also determine F. I'm determining F from the same oscilloscope, from A. I will determine F from oscilloscope A, then from F is equal to 1 over period, and remember the period and the period equals to the time base setting times horizontal distance. So this one you must have seen it in AS waves. The period is the time base setting times the horizontal distance, and the amplitude, which is now the voltage V, is the Y gain or Y setting times the vertical distance. Then step number 4. Step number 4, then you have to look at the other oscilloscope B to determine E. So I will determine I will then determine E on oscilloscope B from, still we find E from the Y gain times the vertical distance. Okay, so we now have E. Now the next step, which is going to be step 5, must be now to repeat steps so that I have different values of F and E. So I will repeat step 4. For different values of I'll repeat step 4, which is finding E, but for different values of F, which has been determined or which is decided on the Y, which is determined on oscilloscope A. I'll repeat step 4 for different values of F determined on oscilloscope A. I'll repeat step 4 for different values of F determined on oscilloscope A and obtain different values of E. And obtain different values of E. So I'm trying to have at least 6 sets of values. So step 6, now it is analysis. I will plot a graph. I will plot a graph. We have already said which graph is going to be plotted. It was ln of E against ln of F. So I will plot a graph of ln of E against ln of F. You can plot also log of E against log of F. So now this is analysis, plotting the graph. We now know which graph we are plotting. The relationship is going to be valid if it is a straight line, which passes, of course, it has a y-intercept, so it doesn't go through the origin, it goes through, it was ln of PV over R. So the relationship is valid if the graph is a straight line. Is a straight line passing through, so it passes through the y-intercept, which was ln of PV over R. Okay. Still for analysis, remember the gradient of the line. We have already showed that the gradient of the line is equal to Q. And we have also said the y-intercept is equal to ln of PV over R, which means that P should be equal to R divided by V times e to the power of the y-intercept. If you have used the log, it will be 10 to the power of the log. But since I've used the ln, so it is e to the power of the y-intercept. Okay, that is for analysis part. Then step 7 for safety. For safety, I've talked about gloves, so I will use rubber gloves. I will use rubber gloves to handle the hot coil, which is especially coil, I think that is coil D. Is it coil D, which is hot? No, coil C. So for safety, I will use rubber gloves to handle the hot coil. And there is, of course, if the resistor so as to prevent burns. If you don't want to use the gloves, you must then be ready to wait to switch off the circuit and wait for the hot coil to cool down. Or I would say, I will switch off. I will switch off the circuit and wait for the hot coil and resistor to cool down. And resistor to cool. I think I'm tired. To cool down. Okay, so what I've written here would give you it has more than 15 marking points, so you can get all the marks for this question, I'm very sure. If you wrote your essay like that, you drew your diagram with all these parts, I think you should get at least 15 marks, if not 14 maybe. Okay, so that is question number 1. Then question number 2, without wasting time. A block of modeling clay of mass m is attached to a string as shown in the figure. Okay. A pellet traveling at speed u enters the block and causes the block to move through a vertical distance h. The experiment is repeated for different values of m. It is suggested that h and m are noted by the equation 1 over h is equal to 2gm plus z over uz squared. A graph of root of 1 over h on the y-axis against m on the x-axis is plotted. So determine the expression for the gradient. So we must make root of 1 over h the subject. So introducing square root to both sides, I have that the square root of 1 over h is equal to the root of twice g divided by uz, then plus times m plus z. So making m the subject, separating m to be alone, I have that 1 over h, root of 1 over h, m, is the same as the square root of twice g divided by uz times m plus the root of 2g over u, because the z cancels. If I multiply uz times 1 over uz times z, it remains root of 2g over u. So if I compare this with the y equals to mx plus c, and they said on the y-axis they are plotting 1 over root of 1 over h, on the x-axis they are plotting m. So when you compare, it means the gradient is going to be root of 2g divided by uz, and the y-intercept is going to be root of 2g divided by u. Okay, so values of m and h are given in the table 2.1. Calculate and record values of 1 over root of 1 over h in the table. Include absolute uncertainties in root of 1 over h. So this is, we are going to just maintain the number of significant figures for simplicity. So these are 3 significant figures each. So I'll simply say the root of 1 divided by 2, 1. So this is 3 significant figures. I'll write this as 0.218 plus or minus. So the next one is going to be, I'll just change this to 1 divided by 17.8. 17.8, which is 0.237 plus or minus. Then the other one is 16.2, which is 0.248, 0.248 plus or minus. The next one is 14.6, which is 0.262, 0.262 plus or minus. Then the next one is 12.6, which is 0.282 plus or minus. And the last one is 10.2, which is 0.313. For the uncertainty, let's say our y equals to the square root of 1 over h. This is the same as 1 over h power a half. So that means the absolute in y divided by y is going to be equal to a half into absolute in h divided by h. So it means the absolute in y is always going to be a half absolute in y in h over h, then times y. So I'll always multiply the absolute over h times a half, then times y. So for example, the first one is going to be the absolute in y is going to be a half times 0.2 divided by 21.0. Then the value of y is 0.218. So let's check that one. 0.5 times 0.2 divided by 21, then times 0.218. So to one significant figure, that is 0.001. So the next one is going to be 0.5 for a half times 0.2 divided by 17.8 times 0.237. So it is also 0.001. The next one is 0.5 for a half times 0.2 divided by 16.2 times 0.248. So this rounds off to 0.002. The next one is 0.5 for a half. 0.2 divided by 14.6 times y, which is 0.262. So this is also 0.002. The next one is 0.5 for a half times 0.2 divided by h, which is 12.6, then times 0.282, which gives us 0.002. And the last one is 0.5 for a half times 0.2 divided by 10.2, then times 0.313, which is 0.003. Okay, so those are the uncertainties. So I'm just going to transfer this table on paper so that I can plot it very fast. Okay, so now I can plot. So I'm going to plot a point and its uncertainty at the same time so that I save time. So we are plotting a graph of root of 1 over h against m. So when m is 565, the scale on the x-axis is 50 divided by 10, which is 5. So this is 55, 60, 65 is here. 65 against 0.218. So I'll say 0.218 minus 0.21 divided by the scale on the vertical. What is the scale on the vertical is 0.01 divided by 10, which is 0.001 on the vertical. So I'll divide this by 0.001. Those are 8 boxes. So the plotted point is going to be this one here. Then the scale, remember, was 0.001. I mean the uncertainty. So 0.001, that is one small box at the bottom and one small box at the top. So one small box at the bottom and one small box at the top. Remember to pass there the pencil twice with the rule, of course, to make this look bold and thick. Then I draw the vertical line. Yours should be better because you're drawing on paper. Make sure the lines are thick. Then the next one was 637. So this is 610, 20, 30, 35. So 37 is somewhere here against 0.237. So 0.237 minus 0.23 divided by 0.001. Those are 7 boxes. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It is after the 7th. Then 1, 2, 3, 4, 5, 6, 7. So I think this is 0.0. This should be a point which is somewhere here. Okay. 1, 2, 3, 4, 5, 6, 7 on the vertical. 1, 2, 3, 4, 5, 6, 7 on the horizontal. That is 1, 2, 3, 4, 5, 6, 7. Okay, so that is the point. Then the error was 0.001. So just make one small square up. and one small square down. Then I draw the vertical bar. Then the next one is 675, which I think is just 5 boxes from 650, because I add 25 here. Then on the vertical, it is 0.248. So this is 241, 242, 3, 4, 5, 6, 7, 8. So this is the point here. And then the errors were 0.002. So I add 2 boxes up. Use a ruler to draw this. And 2 boxes below, use a ruler to draw this. Then I join the bars with a vertical line. Make sure it is bold enough. Then the next one is 0.723, 710, 720, 23. This is 25, so it is between 20, 710, 720, 25. It is against 0.262. So 1, 2, 3, 4. It is in between here. And the other one is 0.262. 261, 262, it is around here. Because this is 720, 710, 720. 23 is around there because this is 25, so it is almost in the center here. Then I plot that point. The error bar is 0.02, so I'll put 2 boxes above and 2 boxes below. This point is almost in the middle of the box, so I'll draw the line here. You draw this using a ruler. Then the next one is 790. So on 750, we got 790. And 790 is against 0.282. 790, so this is 750, 60, 70, 80, 90. Then 0.282, 1, 2. So this is the point. So I'll circle this point here. And the error bar was 0.02. So I set 2 boxes below and 2 boxes above. Remember to use a ruler to make this look neat. Then I draw the vertical bar. Remember to pass the pencil twice so that you get a very beautiful error bar. And the last one was 892. 892, so this is 850 against 0.313. 890, so this is 850, 60, 70, 80, 90. This will be 95, so 92 is somewhere close. But then on the vertical it is 0.313, so I have to count 3 boxes, 1, 2, 3. So it's around here. Okay. Then the error bar was 0.003, so I count 3 boxes at the bottom. 1, 2, 3. So it should be around here. And 3 boxes on top. 1, 2, 3. So this error bar is not exact on that line because it was 2, so I'll draw it around here. You must use a ruler to draw these error bars. Okay. So having drawn the error bars and the plotted points, I'll begin by drawing the line of best fit. I cannot draw the line of best fit if the graph is not fitting on the same page, so I have to minimize this. So I must make sure that all these are on the same page so that I balance the points. If I draw the line of best fit, so my line of best fit is not going to be as accurate as yours because of where I'm drawing. Yours should be better than mine. If you try to sketch to draw this, it should be better. So I'm drawing the line of best fit. Make sure the points are balanced, well balanced points. Try to first put a pencil through each plotted point and see how it behaves. Okay, I think my line of best fit is, yeah, it is acceptable, though it is not well balanced, but I can draw still a better one. Let me try to draw a better one. This is even worse. It's always better you draw the line of best fit with a pencil because you are making judgment. You are trying to balance the plotted points. Do not aim at joining the first point to the last point. That's not the line of best fit. Okay, I'll just go with this one. Although when I maximize it, it was going to leave this point very far, but it's fine. I'll go with that line of best fit. You draw a better line of best fit where the points are well balanced. The next is going to be the line to draw the line of worst fit, which you can even choose a different color for that line. In an exam, you can use a different color because that one you make a judgment once. But of course, you are only using a pencil, black or blue. So you don't need to use any other color. So I have two options, either to draw a line which is steeper or a line which is shallower. So I'll draw the one which is steeper because the one which is shallow is going to be very close to the other one. So let me draw one which is steeper. So I'll draw from the top error bar to the bottom of the bottom error bar. Don't mind about the lines meeting or appearing as if they are converging at the same point. So before you conclude on the line, make sure it crosses through all the error bars. So I see that this error bar is not crossed and this one is also not crossed. Actually, even this one is not crossed. So that line is not going to be good enough. So I have to draw a better line of worst fit. So I have to modify this line so that it crosses through all the error bars. Okay, so let me try to change it. So I'm adjusting my line to touch the second last error bar from the top to see if the rest are also crossed. So in doing so, I notice that my line touches all the error bars. All the error bars. That is very important. There's only one problem, it is not straight, so I have to again to draw another one. Okay, so this one, because it's the line of worst fit, remember, it should touch what has happened to my lines. Okay, so I've decided to rotate the graph so that I have enough space. So I've decided to rotate this graph. So I have to draw again the line of best fit and see, because it seems the line I drew has disappeared. So again, let me draw the line of best fit. So I've tried to rotate my graph so that I have a bigger grid here to draw in. So I have to try and balance the plotted points. Remember, your plotted points should be carefully circled to make them very visible. You should be drawing the line of best fit with a pencil, please, to ensure that your points are well balanced, so that when you make a mistake, you can always rub to ensure that you make corrections. So I'm checking the points to see. Still, this is not satisfactory because it leaves 2 points on one side. So I have to bring in 1 point at least. So I'll bring in the one which is at the bottom, and I ignore the one which is at the top. Okay, I think that is a better line. Then for the line of worst fit, I'll change the color to green. And I said I will join the top. I will join the top of the top error bar to the bottom of the bottom error bar, but I noticed that some of these points are left out. So for instance, this one will be left out, so I adjust my line to ensure that I join the bottom of the bottom error bar. Going through this one, it goes through this one, touches here. I just rotate clockwise to this point here, so that now all my points are on a straight line. So I'll just draw this line which touches through this point and crosses all the vertical error bars. Okay, so you can draw a better line. All that you should ensure is that the vertical error bars are crossed by that line of base fit that you have drawn. So that is going to be my line of worst fit. So you have to label the lines. So I'll label these lines carefully. This one is going to be the line or the best fit. You can just say best fit. And this one is going to be labeled worst fit. The second thing I'm going to do is to draw the triangle for the gradient. So I'll have to increase the thickness slightly so that I have a better visible triangle. So you can use a pencil and pass the pencil twice. So you can choose to draw one triangle as long as you can find 2 points where the triangle can pass. For example, I have this point here and this one here at the top. Then at the bottom, if I fail to get 2 points at the bottom, I can still break down my triangle at the bottom so that it is the same triangle on the top, but it breaks down at the bottom. So I can draw a vertical line here for the triangle. I'll use dotted lines for the triangle. But when I reach the bottom, I'm going to break it into 2. I'll use this one for the line of worst fit. And I'm going to use another point for the line of best fit. For example, I can use this one here for the line of best fit. Okay, so there are 2 triangles in one. Okay, so the next thing is the gradients. So for simplicity, I will do the gradients here so that I just transfer them on the page where we are supposed to find. I'll just do them on here so that we just transfer them on the page where we're supposed to write the gradient. So of course we're not supposed to do your work in here for the gradient, but because I want people to see what I'm doing, I'll do it here. So I'll say gradient for the best fit. is going to be the change in the y values. So we have the y values, that is 0.3. No, that is for the worst fit. For the best fit, it is 1, 2, 3 points below. 1, 2, 3. It is here. So from my calculator, 0.313301302, that is 307. So this is 0.307 minus, on the y-axis, I mean at the bottom here we have 0.2221, 221, 0.224. Divide by, on the x-axis we have 50, 50, 60, 70, 80. So that is 880 minus, we have, this is 50, 60, 70, 80, 85. I mean 55, 585, I think. Yeah, 550, 60, 70, 50, so 60, 70, 80, 85. So there's 585. So that is for the best fit. Then for the worst fit, on the y we have 0.310 minus 221, 222, 223, 0.223. Divide by the x-axis, we have 880 minus, I think the x-axis is almost the same. It is here. So it is 585. On the x-axis, it is 585. Okay. So these are the values I'm going to transfer on the other page for the gradients. I'll just record them on paper so that I don't need to return here. So 0.307 minus 0.224 divided by 880 minus 585, 0.310 minus 0.223, 880 minus 885. I mean, sorry, this is 585. This is 585. Okay, so I'll rotate back. Okay, so here they want us to find a gradient. We have already found our gradients. I'll try to make this one bigger to fit into the page. So you tell the examiner that the gradient of the best fit equals to, we saw 0.307 minus 0.224 divided by 880 minus 585. Then we saw also that the gradient of the worst fit was 0.310 minus 0.223 divided by 880 minus 585. So I'll just press my calculator. You don't expect to get exactly the same answers like mine, because for you are plotting on a paper, 0.307 minus 0.224 divided by 880 minus 585. So this is going to be 0. I'll just write 2.81 times 10 to the power of times 10 to the power of minus 4. And then this one, 0.310 minus 0.223 divide by 880 minus 585. So this is 2.95 times 10 to the power of minus 4. Then they said include the absolute uncertainty. So we'll tell the examiner that uncertainty equals the difference between those two. So it is 2.95 minus 2.81, of course, times 10 to the power of minus 4. So 2.95 minus 2.81. So that is 0.14 times 10 to the power of minus 4. So I can write my answer here as 2.81 plus or minus 0.14. This is times 10 to the power of minus 4. That is going to be the gradient and its uncertainty. Okay, I hope I've tried my level best to be accurate. The next is determine the y-intercept of the line of best fit. Include the absolute uncertainty in your answer. So for y-intercept, we shall use y equals to mx plus c. Don't read the y-intercept from the graph. So we'll get c for best fit, which is going to be the y value minus m times the x value. So I'll just use the same values that I've used for the best intercept. So I'll take these values here. So the y value is going to be 0.307 minus, remember the gradient was 2.81 times 10 to the power of minus 4, then times the x value, which is 880. So I have 0.307 minus 2. I'll start with 880 times 2.81 exponent minus 4. So the y-intercept here is going to be 0.05 to two significant figures, 0.0597 to three significant figures. Then I'll find C for the worst fit. C for the worst fit will still use the same formula, but I will choose a pair of values from the worst gradient, which is this one here. So I'll take the y value was 0.310 minus the gradient for the worst fit was 2.95 times 10 to the power of minus 4 times the x value, which is 880. So I'll start with the bracket 880 times 2.95 exponent minus 4. Then I say 0.310 minus the answer. So this is 0.0504, 0.0504. Then they want to include the absolute uncertainty. So I'll say uncertainty is going to be the difference. So 0.0597 minus 0.0504. So 0.0597 minus the answer. So it is 9.3 times 10 to the power of minus 3, or which is 0.00093. Yes, there are two zeros, so 0.0093. So the y-intercept is going to be 0.0597 plus or minus 0.0093. Use your answer to A C Roman 3 and C Roman 2. Determine the values of U and Z. Include appropriate units. Okay. So remember earlier on we saw that the gradient was equal to the gradient was equal to, it was, I think, root of twice g divided by u times z. That was the gradient. So they have given us g 9.8 and we want to find u. So making u, do I have z? Then we also mentioned above here that the y-intercept is root of 2g over u. Okay, so I'll start with the y-intercept then. The y-intercept is root of 2g over u, so I can find u first. So it means u is going to be the square root of 2 times 9.81 over the y-intercept, which is over 0.0597. That is the y-intercept. So this is the y, this is going to be u. So 2 times 9.81 square root of the answer divided by 0.0597. So this is 74. It's actually 74.2. Then z, so I'll make z the subject. So z is going to be equal to the square root of 2g divided by u times the gradient. So which is going to be the square root of 2 times 9.81 divided by u, which is 74.2 times the gradient. And our gradient was 2.81 times 10 to the power of minus 4. So this is 2.81 times 10 to the power of minus 4. Okay, so I'll just say 74.2 times 2.81 exponent minus 4. Okay, then I open brackets, the root of 2 times 9.81. Then I close the bracket, divide by the answer. So this is 212.4. So this is 212.4. Okay, so I have 74.2 and 212.4. What is missing is now the units. So I will calculate the units. So the units for u, we have centimeters per second, but this is under the square root, so this is power half, divided by the y-intercept. Of course, the y-intercept was power, minus centimeters power half, minus a half, divided by centimeters power minus a half. So when I open this bracket, is centimeters power a half times s power minus 1 divided by centimeters power minus a half. A half plus minus a half minus minus a half, it becomes centimeters. So the units here are going to be centimeters per second. Then, so this becomes centimeters per second because a half minus minus a half, it becomes power 1. Then for z, since I know the units for u as centimeters per second, so for z I have centimeters per second squared, that is g, and as power a half divided by centimeters per second. Then the gradient is, so for the gradient I have as I have per centimeter power minus a half, that is on the vertical, per centimeter power minus a half on the vertical for the gradient. divide by, on the x-axis it is, I think it is m, which is what? Which is grams. Divide by grams. So this is going to be centimeters per minus a half. Grams goes up, or divide by g. Okay. So centimeters, I have to do the algebra here. So this becomes centimeters power a half times s per minus 1 divided by centimeters per second, then times centimeters per minus a half, then g goes up. So per second has cancelled. Centimeters power minus, I think centimeters has cancelled because when this goes up, it becomes centimeters over centimeters. So z is just going to be g, grams. Z is going to be grams. Okay, so Z I remain with the grams because all these ones cancel out. Then determine the percentage uncertainty in Z. Percentage uncertainty in Z. So you have here so many options. For instance, when you look at the general expression, we said that the root of 1 over h is equal to the root of 2g, I think, into m plus z over uz, which meant that, well, what is that expression? I don't want to go back to Genesis. Okay, so we can say um, m is the gradient, this is the y-intercept, so z, if I make z the subject here, you notice that z is going to be equal to, because this is the gradient and this is the y-intercept, so it means z is going to be equal to, let me just use the expression for gradient, it is going to be enough. So the gradient was equal to the square root of 2g divided by u times z. Okay, u has an uncertainty. Do I have u? So it will be the absolute uncertainty u plus the absolute uncertainty in the gradient. Okay, for the gradient it is easy to find. I have it, so I don't want to use that formula. Let me use the one for the y-intercept. I don't want to do this twice, so I'm going to use the expression which has a y-intercept and the gradient at the same time, because I have the uncertainties for the gradient and that for the y-intercept. So when you look at this equation here that we have just written here, you notice that if I make z the subject, because this is gradient, this is root of 2g over y uz is the gradient, and the gradient equals to the square root of 2g over uz, and then yet u is equal to the square root of 2g over the y-intercept. So if I combine these two here, it means when I make here z the subject, z is going to be equal to root of 2g over the gradient times u, which is the same as the root of 2g divided by the gradient. Where there is u, I'm going to put root of 2g over the y-intercept. So the y-intercept goes up. So it means z is going to be root of 2g cancels that up. So z will be the y-intercept divide by the gradient. If you notice that z will be the y-intercept divided by the gradient. So I'll simply say percentage uncertainty. The percentage uncertainty in z is the same as the percentage in the y-intercept plus the percentage in the gradient, which is simply going to be the absolute in the y-intercept. Then we divide this by the y-intercept plus the absolute in the gradient. Divide this by the gradient. Then we multiply this by 100. So this will be for the y-intercept. Remember the y-intercept was 0.0093 over that. So I'll just simply say 0.0093 divided by 0.057597 plus for the gradient, remember for the gradient was 0.14 divided by 2.81. The power of 10 will just disappear. You will not consider it. So it is 0.14 divided by 2.81. I'll multiply this by 100. So this will be a percentage. So this is going to be 0.0093 divided by 0.0597 plus 0.14 divided by 2.81, then times 100. So this is giving me 20%. So this is 20%, approximately 20% or 20.6%. Okay, so the percentage uncertainty in Z is 20.6%. That is quite big, but you may get a value which is as low as 5%, depending on how you have calculated this. I'm just interested in the method. Then the experiment is repeated, determine the mass m that gives a value of h of 25 centimeters. So go back to the original equation. It was 1 over h is equal to g into m plus z divided by uz squared. So determine the mass m that gives a value of h of 25.0 centimeters. So I'm going to make m the subject here. When I open the brackets, you notice that 1 over h under square root. Then I multiply this by, so divide by root of 2g, then times uz, then I subtract z. This should give me m. So I'm making m the subject. So m is going to be uz divide by, because root of 1 is 1, so the other one goes into the denominator, so it will divide by root of 2gh, then minus z. So I'll just substitute. I'll just take in the values of u, which is 74.2, z, which is 212.4, then divide by the square root of 2 times g, which is 9.81. Is it 9.8? Yes. No, it is. Yeah. I've been using 9.81 instead of 981. Sorry, I have to make some small changes here. This is 981. So my answers should slightly change. Sorry for that. I don't know how I saw 9.81. Okay, my answers will slightly change. Therefore, sorry for that mistake, because I do this naturally. So 2 times 981 square root something is wrong with my device now. So divide by 0.0597. So this is supposed to be 741. Of course, the units are not going to change. Then this one is also going to change, I think. 981. So this is 2 times 981. Root of the answer, divide by, this was 10 to the power of minus 4. So it is divided by 7, 4, 1, not 4.1.2. So it is 7. Very confused now. I'm very tired. So it is, the first one is root of 2 times 981, root of 2 times 981, then divide by 0.0597. So that is 742. So this is 742. Again, I'll say root of 2 times 981, divide by open brackets 742 times 2.8 exponent minus 4. Okay, so that is 213. So this one has not changed much. So it is 213. Okay. So that is 213 grams. Okay, so here this one has not changed. It is only this one which must change. So this is 742 and 213. Yeah, this happens in an exam. Sometimes we make such mistakes. So 742 times 213, 981. So 741 times 213 divided by the root of 2 times 9.8, sorry, 281. Yeah, so that is going to be 3000 or 3.6 times 10 to the power of power 3 grams. Okay, so that is, of course, these are just rough answers as long as you get the method correct. So that will be the final mass in grams. Yeah, you can still go through this and see where I have made mistakes. You can always raise questions. I am ready to always answer some questions. Until next time, I'm very tired. Bye bye.